Well, I hope you're doing well, and we're into our last full week of classes now. So, just wanted to let you know that I'll just be doing 3 more lectures, and as much as we get through on Friday is as much as will be on our final exam. So, just a couple more of these to keep track of. As always, feel free to go join our Google Hangouts if you have questions. Anything you'd like to email me as well to get together to talk about stuff, feel free. But hope you all are well. Hope you're keeping up with all your schoolwork. And next week is going to be reading day, and then your final exam schedules will start. So you're just about there, almost done. All right. So I thought I'd share another couple of fish pics with you. This is a site that we were sampling when I was in Nepal. We're up at about maybe 8,000 feet or so, and sampling an area that the waters were really flowing pretty rapidly. You can see in the background there. We couldn't net those areas obviously, so we were standing near shore to catch fish. And these are one of the things that we caught. So you might look at those and think, those don't even really look like fish. And in fact, only one of them is a fish. The one on the right is a fish. The one on the left is a tadpole. Yeah, it's actually a tadpole. But the one on the right is a catfish. And now both of these critters have suction cups on the underbelly that they use to hold onto rocks in high flow to keep from getting washed downstream. So kind of an interesting physiological adaptation. But when you look a little more closely, sure enough, it's a catfish. This is a side view of it. It's just a very flat catfish that can stay out of the flow to keep from getting washed downstream and stick onto rocks with their suction cups. So it's a pretty amazing adaptation. So last time we were talking about types and sources of air pollution, and we mentioned a few of these pollutants that were greenhouse gases, those highlighted in green. And I mentioned there are 6 pollutants that the EPA is required to monitor. And so here they are: carbon monoxide, sulfur dioxide, nitrogen oxide. Both of those, remember, important for acid rain. Tropospheric ozone. Again, ozone is good news when it's in the stratosphere, but bad when it's in the troposphere. Particulate matter, and then lead. So there's one molecule that was on the EPA's list briefly during the Obama administration. It was put on the list and came off again once Trump came into power. But so carbon dioxide was on that list, and it's a curious case in some ways because carbon dioxide is a natural byproduct of respiration, right? So it's not like mercury in the atmosphere where it's all come from human production. But the reason that carbon dioxide was termed a pollutant was because of climate change. And so that's our topic for today. So, global climate change is really something that has gotten stuck in a big political debate. But as scientists, we just want to look at the data. We just want to look at the data and see what the data tell us. And so, if you look at what temperatures have done through the 20th century, essentially, the deviation from the average starts to get pretty great in the latter half of the 20th century. Now, atmospheric scientists are great at using models to forecast and to explain, in fact, what's happened already. And it turns out that the pink bars there, the pink polygon, is the range of temperature estimates using both natural and human-made forcings. In other words, natural and human activity that will affect the climate. The blue is the range of predictions from models only using natural forcings. And so the main point here is that after the 1950s, we really can no longer explain the warming that the Earth experienced except to take human activity into the picture. And these are data contained in the Intergovernmental Panel on Climate Change's 2007 report. Now, greenhouse gas levels have fluctuated, as have temperatures. So if we just look at the temperature bar, the bottom bar there, this is a graph that goes back about 500,000 years. Now, we have really good data going back about 500,000 years because that's how long our current ice caps have been where they are. So we can take core samples of that ice and analyze the bubbles in that ice, even analyze the ratios of different chemicals in that ice, and get pretty good estimates of what the temperature was like. Now we can also get pretty good estimates of what the carbon dioxide levels were like. And when you look at the two plotted next to each other, you can see that there's a pretty tight relationship. That time periods through history when temperature was warmer were also times when carbon dioxide was warmer. And similarly, lower temperature were times of lower carbon dioxide. And again, humans have been on the planet, the earliest fossils we see are about 200,000 years ago. So this is going back before human history. But if you just look at the blue graph of carbon dioxide, see how it starts to go straight up toward the end of that graph. That's why people are a little worried about effects on the global climate, because we now have higher carbon dioxide concentrations in the atmosphere than we've ever had at any point in human history. Now, there are some times going back millions of years when carbon dioxide levels were higher, but humans weren't on the planet. But so again, there's this tight relationship between carbon dioxide and global air temperature. Zooming in a little more closely, if we look toward the end of the 20th century, we see that our global CO2 concentrations went from about 315 to 375 or so in the last half of that century. So increase in about 60 parts per million of CO2 in the atmosphere. And it's kind of interesting when you see these annual fluctuations as well in CO2, where CO2 is higher in the winter and lower in the summer. Why do you think that might be? Why might our global atmosphere have more CO2 in the winter than the summer? Well, it's because the big deciduous forests of the global north lose their leaves in the winter. So in the winter, they're not able to suck that CO2 out of the atmosphere. So the global CO2 levels go up. Then again, in the summer, those trees get their leaves, they take the CO2 out of the atmosphere, and it drops down again. And we've got something on the range of maybe 7 or so parts per million variation from summer to spring. So it just shows the role of trees in regulating the amount of CO2 on the planet. Okay, so why does more CO2 mean warmer temperature? Well, it's because of something called the greenhouse effect. This is something that was documented over 100 years ago by the Swedish scientist Arrhenius. And what he showed is that carbon dioxide as a molecule has the ability to capture heat. So you see these little CO2 molecules, the red are oxygen, the white is carbon, right? When those are in the Earth's atmosphere, what happens is that it's like a greenhouse. So if you've ever been in a greenhouse that has glass, it's the same reason that your car gets really hot on a warm day, right? The sun's energy in the visible spectrum passes through the glass. All right. But the heat can't get back out through the glass. And the reason for that is that the sun's rays warm, let's just talk about the car for a moment, the sun's rays warm the interior of that car. That's why, the seat of your car, right, anything metal in your car, the seat belt buckle, if it's been in that car for a while in the summer, it's going to get really hot. So the sun is warming the interior of that car. But here's the thing. The heat radiates off the inside of that car as infrared heat, right? So infrared heat is longer wavelength. Infrared heat is not able to escape back out through the glass. And so that's why the inside of your car gets much hotter than the outside climate when the sun is allowed to come through the windows. So now think of the Earth's atmosphere as the glass in those windows. So the Earth is able to absorb the visible light of the sun, which passes through the atmosphere. Of course, we know that because we can see that light coming through. But then when the sun's rays warm the surface of the Earth, that heat is radiated off the surface of the Earth as infrared energy. And that infrared energy is not able to get out past these carbon dioxide molecules. They are able to absorb the heat and radiate it back. So it's because of carbon dioxide and a couple other gases as well that we have the greenhouse effect. Now I might just mention in passing that the greenhouse effect is a good thing. If it weren't for the greenhouse effect, our atmosphere on Earth, our temperature on Earth would be about 50 degrees Fahrenheit cooler. So it'd be really hard to live here. But the problem is, as we put more and more CO2 into the atmosphere, and how does that happen? Well, it's from burning fossil fuels, right? It's that carbon cycle. Remember that carbon cycle from earlier in the semester? As we put more and more CO2 in the atmosphere, it increases the ability of the atmosphere to retain the Earth's heat near the Earth's surface, and that leads to a warming in the climate. So again, another look at global temperatures from some ice core data going back about 500 million years. And so you can see that there have only been a few time periods when the Earth has been warmer than it is now. So what we would say is that we're currently in an interglacial period, because each of these times of very low global temperature corresponded with a time of very high ice volume. And so you can see toward the end of the graph, on the right side of the graph, our global temperature was already relatively warm even before we started putting a lot more CO2 into the atmosphere. Okay, so the climate's been changing quite a bit throughout history, right? Even before people started putting CO2 into the atmosphere. So what has caused climate change? Well, there's a few things. And I'll go through each of these separately, right? So we'll begin by talking about variation in the Earth's orbit. These are what are known as Milankovitch cycles. So the orbit of the Earth around the Sun is not perfectly round, and it's also not consistent. So because of that, the shape of the Earth's orbit varies over time. And so this is really responsible for the cycle of glacial and interglacial periods. So there was a Soviet scientist named Milankovitch, and he figured this out mathematically, and it's pretty complicated. I cannot understand it myself completely, much less explain it to you, but suffice to say, the shape of the Earth's orbit varies cyclically. And based on the shape of the orbit, it determines how close the Earth is to the Sun. And how close the Earth is to the Sun determines, of course, the warmth of the Earth. And that, in turn, affects these cycles of glaciers. All right. Well, volcanic activity can also play a strong role. And we have a couple examples of this through history. So the Tambora volcano in Indonesia lowered our global temperature by 5 degrees Fahrenheit in 1815. So what happens in a volcanic eruption is that all these particles are emitted up into the atmosphere. They get suspended in the atmosphere, and they block sunlight. And so anything that blocks the amount of sunlight that gets to the Earth is going to lead to cooling. But interestingly enough, those aerosols just means like particles suspended in the atmosphere. But once those aerosols eventually settle out, then you can actually get a warming effect of volcanoes, because the eruption often emits a lot of CO2 into the atmosphere, which, of course, again, as we mentioned, is a greenhouse gas. All right, so there are a few other greenhouse gases that we want to be concerned about besides CO2. So methane, nitrous oxide, ozone, halocarbon gases, and then water vapor. So methane is, if you've ever heard of natural gas, that's essentially methane. So it's associated with fossil fuel deposits. It's emitted by cows. So, for instance, if we look at what creates methane, it's respiration, it's decomposition in the absence of oxygen. So what we call anaerobic respiration. It's just like what happens in the stomach of cows produces methane. But similarly, landfills and some agriculture practices will generate it as well. So nitrous oxide, we talked about this already in the context of acid rain. But nitrogen is the component of a lot of fertilizers that we use. So feedlots that are going to have a lot of animal waste, synthetic fertilizers, all of these are going to be ways that nitrous oxide is able to get up into the atmosphere in pretty massive amounts. So ozone, interestingly enough, is also greenhouse gas. And so we talked about how ozone is produced when hydrocarbons, different pollutants in the atmosphere, react with the sun's ultraviolet radiation. Chlorofluorocarbons, halocarbon gases, as they're also known, are also greenhouse gases. We talked a little bit about them the other day as well. And we don't have to worry about them as much due to the Montreal Protocol. They're declining both in production and abundance in the atmosphere. But these are things that were used as propellants in spray, as refrigerants, and those kinds of things. And then just a little bit about water vapor. It's the most abundant greenhouse gas. It contributes greatly to the greenhouse effect. But we're not worried about it a lot for two reasons. One of which, it doesn't seem like human activity is really affecting the amount of water vapor in the atmosphere. The second part is that when you have a lot of water vapor, it is a greenhouse gas. But it also is going to increase cloudiness. And so when you have more clouds in the atmosphere, of course, you're going to allow less of the sun's rays to penetrate to the Earth's surface. So that might have sort of a cooling effect overall. So let's take a look at these different greenhouse gases and how their concentrations have changed from pre-industrial time to the present. So, if you look at all of them, they've increased pretty dramatically. But which have increased the most? I mean, the CFCs, chlorofluorocarbon 12 and 11, started from 0. But just notice the units there. We're talking about parts per trillion, so not a whole lot. Methane and nitrous oxide, talking about parts per billion, and CO2, we're talking about parts per million. So each of those units is 1,000 times more concentrated than the previous one. So methane, for instance, has doubled up to almost 1,800 parts per billion, but that's only 1.8 or so parts per million. So there's not nearly as much methane or nitrous oxide as there is carbon dioxide. However, here's an important point. Some greenhouse gases have greater effects than others. And so we say that those gases have higher greenhouse effect potency. So it turns out that methane and nitrous oxide have higher greenhouse effect potency than CO2. That is, a given molecule will have a greater effect than CO2. However, because their concentrations are so much less, overall they actually have less of an effect. All right, so we've talked already about this idea that we can only explain what the temperatures have done in the end of the 20th century by taking into account human activity. So let's take a little closer look at those data. So these are data from the mid-19th century to the beginning of the 21st century. And if you look at our global average sea surface temperature there on the top, it started increasing around 1900, and so if you look from 1900 to 2000, there's been about an increase of about 1 degree essentially throughout the 20th century, right? Approximately 1 degree. Now, another important piece of climate change is sea level change, and so again, if we look throughout the 20th century, 1900 it was at this is the difference from 1960 averages, right? So we were at about 100 millimeters below to about 50 above. So we've increased our global average sea level by about 150 millimeters, right? And how much is that? That's somewhere on the order of 5 inches or so, right? So this is definitely a trend, right? We had this increase of 5 inches in our global sea levels throughout the 20th century, and an increase of about 1 degree Celsius in our global average surface temperature, and those increases have continued. All right, so I like visuals, and I think I've told you all National Geographic is my favorite magazine of all time. And so they had a really neat article with some great visuals to kind of help us conceptualize what climate change is doing. And so in this graph, they looked at every year from 1880 to 2016. And they have the average of the 20th century right there at that 0 bar on the y-axis. And then they plotted how far each year was below or above that average. And so the ones that were below the average, of course, are in blue. The ones that are above the average are in red. And, this is the kind of thing, you can show to a 4-year-old and they'll tell you what's going on, right? There's a lot more blue on the left side of that graph, which means that temperatures were all below that 20th century average until what? About 1940. Then there was a warm period. Then between 1940 and, about 1970 or so, it was kind of back and forth. It wasn't too far off the average. But then, especially once we get into the 1980s, it's been consistently warm, right? And in fact, the 3 warmest years on record were 2016, 2015, and 2014, right? With 2016 being 1.7 degrees above the average. So clearly there's been a warming trend that's continued into the beginning of the 21st century. Looking at those atmospheric CO2 concentrations, again, if we were to take the 19th century average, it's about 290 parts per million, and we're up over 404 now. Right? So a lot more CO2 in the atmosphere than we had back in the beginning of the 20th century. Now it's kind of interesting to look at where the CO2 emissions have been coming from. And so it's a little bit after 2005, China actually surpassed the United States as being the largest global carbon dioxide emitter. Now, they have a lot more people in China than the U.S., so the amount of emissions per person is still highest in the U.S. But it's kind of encouraging to see that emissions in the U.S. have actually been dropping since 2005. Do you wonder why that is? Well, a big part of that has been our switch from coal to natural gas. Natural gas is more efficient, has a lower greenhouse gas, a lower carbon footprint. So that's played a role in dropping our CO2 emissions, right? So people that say that we can't drop our CO2 emissions, it'll change our quality of life. We've seen it already in the last 10 years or so in the U.S. All right, so what are temps predicted to do? It's going to depend largely on how economies around the world grow through the next century. But even in a scenario of the lowest possible emissions, we're projected in most parts of the states to have between a 3 and 5 degree increase in average temperature by the end of the century. Now that's the best case scenario. What's more likely is a change between 7 and 8 degrees. So we're going to be seeing some big changes, and the next lecture we'll talk about how we're already seeing changes, for instance, in the way our ecosystems work in response to temperatures. So this is what's predicted to happen. This is a global map of those predictions, and the main point I want you to get out of this is that the areas predicted to warm the most are at high latitudes, right? So if you look at the purple there on the right, these warmest areas are going to be at high latitudes. Now that's problematic for 2 reasons. Number one, that's where a lot of our ice caps are, and so those ice caps are going to melt. And so that's going to have implications for sea level change as well as a habitat for species up there. The other thing it's going to do is that ice functions like a mirror. And so when the sun shines down on ice, most of that energy gets reflected back up, right? But then when that ice melts, what's underneath it is a lot darker. And so increasing the temperature in these higher latitudes is going to have a positive feedback effect, where that's actually going to cause the atmosphere to warm more because of exposing these darker surfaces and eliminating that reflective coating of ice. If you look at what temps have done in the US, these were average temperatures at the beginning of the 21st century compared to averages in the first half of the 20th century. And the main thing I want you to notice here is just how much variation there is. You know, if you were living in Troy, Alabama, and you said, you know, I don't think this global warming thing is true. It's actually cooler now than it ever has been. You would have been correct, right? Because it actually decreased the average temperature by about 0.5 degree in the beginning of the 21st century relative to the 20th. But most places in the U.S. were definitely not following that trend, right? And so certain places in Minnesota and Colorado actually had average increases up over 3 degrees. But it just points out that the reality of the climate that people experience can be very different, even though the global average has certainly been increasing. So as I mentioned, a part of this climate change is leading to rising sea levels. So as these glaciers and ice in other parts of the globe melt, that will cause more water to flow into the oceans. And as oceans warm, they expand. So what's interesting is that when you look at the sea level rise, this is a graph we looked at earlier, and you look at what caused most of that sea level rise, what do you see there? Yeah, thermal expansion is actually causing the sea levels to rise more than actually increased meltwater. So you know, as things warm, they expand, right? As gases warm, they expand. Similarly, as liquids warm, they expand. And so this warming of the sea temperatures is causing the sea to expand, and that is actually driving the most sea level rise. So some consequences of this are increased erosion, coastal flooding, and as the level of those oceans rises, the salt water is able to penetrate into some of our freshwater aquifers, and so that can be problematic for our water supply. Sea level rise is another area where we've been revising our estimates. So up through 2009, sea levels were rising on the average of about 1.7 millimeters per year. Recent data have shown that now, in fact, it's at about 3.3 millimeters per year. So, you know, it's, again, this sort of positive feedback mechanism. And so it's not just that there's more water, but that it's different water. So as carbon dioxide increases, a couple of things happen. So oceans absorb about 1/4 of the CO2 that goes into the atmosphere. And for a while, people were puzzled at why the Earth's temperature wasn't warmer than it was. And it was because a lot of the CO2 going into the atmosphere was being taken out of the atmosphere by the oceans. There's an equilibrium between the surface of the water and the atmosphere. So when you have CO2 in water, it dissolves to produce carbonic acid, like we talked about in rain. And this is problematic because corals are very important economically globally. But corals make their shells out of calcium carbonate. Well, there's some chemistry involved here, but suffice to say that when there's more CO2 in the water, it makes it very hard for corals, but not only corals, things like clams, mussels, oysters. It makes it harder for them to create their shells out of calcium carbonate. And so this has the potential to have some negative impacts on coral reefs. In fact, one of your readings is about coral reefs. All right, so you might ask the question, are we responsible for climate change? So the Intergovernmental Panel on Climate Change, which is a nonprofit group of scientists who are studying this, it's under the aegis of the United Nations, concludes that it's more than 90% likely that most of the recent global warming is due to humans. At the G8 summit in 2005, the national academies of 11 nations, including the United States, issued a joint statement urging political leaders to take action. So there's scientific consensus now that this is a human-caused issue. However, because of the change to energy policy, which would be required to really bring renewables online and reduce the amount of CO2 that we're producing, climate change can get stuck in a political debate when the science, in fact, is quite clear. So you can ask the question then, should we pursue mitigation or adaptation? So mitigation is the idea that we should pursue actions that reduce greenhouse gas emissions in order to lessen the severity of future climate change. So the easiest thing to do here is to switch off of fossil fuels used for energy and reduce deforestation so that we're able to keep the trees on our landscape that are taking that carbon dioxide out of the atmosphere. So that's what we can do to kind of reduce the severity. Adaptation, on the other hand, is saying, look, we have to realize that climate change is happening and pursue strategies to deal with it. So we really have to do both. We have to pursue policy that will change our energy strategies to one that is sustainable and will protect the climate. But at the same time, we need to do things like consider where to develop on the coast and come up with some strategies to try to minimize climate change impacts. And one of your readings about the work that mayors and governors are doing to combat climate change has some kind of neat examples of this. But the part that can be forgotten in this debate about climate change is the ethical dimension. So this is a map that's been made to highlight a global disparity. The map on the top, the countries are swelled in proportion to the amount of carbon dioxide that they produce, the amount of carbon that they produce. And so it's what you'd expect, right? It's what the quote-unquote global north, right? It's the United States, it's Western Europe that are producing the most carbon continents, right? Like South America and Africa, hardly any produced at all. Okay, but then when you look at the bottom, it actually shows the predicted mortality that these countries are expected to experience as a result of climate change. And when you look at that, you see that Africa is predicted to have the most increased mortality. There's going to be likely more severe droughts based on forecasts of climate and just more temperature extremes. Likewise, India is much larger. On the other hand, the countries that are producing the most carbon are not those that are predicted to suffer from it. So the question is then, do these countries that are producing the most carbon but are not predicted to suffer the most from it, do they have an ethical responsibility to take into consideration those other countries? And I would argue that they do. This is an article from The Lancet, which is a medical journal. And they argue that climate change is the biggest global health threat of the 21st century. They talk about diseases being able to move different parts around the globe, that vectors of diseases like mosquitoes and other things are going to be able to move to different parts of the globe. I don't know. I wonder with corona if there's a way that climate change relates. I don't know. I think obviously corona, you could argue, is the biggest global health threat of the 21st century now. But climate change is a big issue. And climate change is a continuous issue, right? We're hoping we'll be clear of this COVID-19 thing, and who knows, 6 months or a year, who knows how long. But climate change is going to keep on going, and it's going to cause misery for a lot of people. So when this article was published, the 12 warmest years on record in the last 150 years had come within the last 13 years. And these doctors say health impacts will be felt all around the world and not just in some distant future, but in our lifetime and those of our children. So this is really an ethical issue that we have to confront, and many would argue kind of the biggest ethical issue of our current age. So we have to get past the political posturing and arguments and look at the data, because after all, this is a scientific question. And there's an article that's on Moodle to read for the final exam where Naomi Oreskes outlines the scientific consensus on climate change and kind of lays that case out. So I hope you all are doing well, and I'll look forward to seeing you again soon.